Okay, we are continuing with the recording where we left off. As I said, I had to address something real quick because I kept getting emails. I was recognized for something, so people were emailing me to congratulate me. So that's why I had all the extra emails. Anyways, we are looking at intermolecular forces, and this is where I left off. So remember, the physical state is affected by the intermolecular force. This force here is a type of attraction. Okay, an attractive force. This will also affect the boiling point and the melting point of the chemical. So we're told here intermolecular forces, these are attractive forces that exist between molecules. So we're being told what these intermolecular forces are, what we're going to be looking at, and we're told they're in the order of increasing strength, meaning that the hydrogen bond is the strongest, and then the London dispersion force is the weakest. So let me introduce some acronyms here that chemists use because sometimes we're just lazy because we're writing a lot. London dispersion force is usually referred to as LDF. Some people refer to it as dispersion. Dipole, double D. Of course, this is your intermediate, the one in between, mediate. Hydrogen bonding HB, this is the strongest. Okay, so you want to be aware of that. London dispersion force, dipole, hydrogen bonding. These are incremental. Not only are they incremental, they are also additional or additive. So as I go through, I will itemize and list which forces we're dealing with. We're told the strength of the intermolecular forces determines whether a compound has a high or low melting point, boiling point, and thus whether it's a solid, liquid, or gas. That's why we're learning this. The more intermolecular forces, the more energy it requires to melt something or boil a compound. Okay? And the more intermolecular forces, the most likely case will have a liquid. The highest intermolecular forces go with the solid. So let me add that here real quick before I go into what I wrote yesterday. Okay, so we're back here. So we have here greatest intermolecular forces result in most likely having solids. Okay, so if you have the greatest intermolecular force, you're going to have a solid. And then the opposite is true. Smallest or least, right? Smallest intermolecular forces, if I can spell, result in gases. So the gas phase. Okay, what about melting point? Greatest, I'm going to abbreviate, intermolecular force results in higher density, usually higher density, highest boiling point, and melting point. Okay, so I'm trying to abbreviate things because I'm trying to get through this part quickly. Okay, and then of course the opposite is true, right? If you have the smallest intermolecular force, so smallest to least intermolecular force results in lowest density because the molecules are far from each other, lowest boiling point, and melting point. Okay, so now that we're done with this, I'm going to scroll down and see. Now we're going in order, starting with the weakest. This is the weakest of the intermolecular forces. By the way, I wanted to mention this. The intermolecular forces we're looking at, these intermolecular forces exist in covalent compounds. Remember, covalent compounds, these are the compounds that are made up of, compounds. These are the non-metal and non-metal compounds. So they're usually made up of non-metals. So you want to itemize, go through and look at the elements in the compounds. Are they all non-metals? Check. If they are, then you want to assume they have these intermolecular forces. The weakest of the three forces we're looking at is London dispersion force, LDF. All covalent compounds will have this force. Now we're talking about once the compound is made, it's not this is not the force, the bond. No, no, no. The bond is something else. Covalent bond is what makes the compound. Once the compound is made, one compound will attract another compound, or one element will attract another element. So we're seeing here that London dispersion force exists in all covalent compounds. I gave you an example here. As long as it's nonmetal and nonmetal, it qualifies. P2O5, nonmetal, nonmetal, right? CCl4, nonmetal, nonmetal. CO2, you can have two elements, you can have three, you can have 100 different elements. As long as they're all nonmetals, they are covalent and they have LDF, London dispersion force. We got H2O here. And then I move on to the elements that do have London dispersion force. We have elements that have London dispersion force. These elements have to be non-metal also, because the metal elements have a force called, wait for it, metallic, right? It goes with the name. Metallic elements have an attractive force called metallic force. But with the non-metallic elements, the attractive force is London dispersion force. You can't just say molecular force. You can't just be making things up, okay? So we're moving on over here. We have, oh, what did I use? What did I just use? I meant to use this. Okay. Oh, snap, guys. I'll figure this out. The elements are xenon, group 8 elements, nitrogen, oxygen. So essentially, these elements also have London dispersion force as their only force of attraction. So then we're moving on to the other ones, and we're told here that the intermolecular force of attraction in a covalent compound is incremental, meaning that there's a prerequisite force before we have other forces. Okay? As we're dealing with the dipole-dipole force of interaction, or interactive forces, we recognize that molecules that have dipole-dipole have LDF and dipole-dipole, because LDF is a prerequisite intermolecular force before you even have dipole-dipole. So a molecule will not have dipole-dipole and then not have LDF. Okay, they'll have DD and LDF. They have both of them. Okay, if it has this, it also has that. Okay, that being the case, you have P2O5 that has LDF and dipole-dipole, H2O that has LDF and dipole-dipole, HCM that has LDF and dipole-dipole. Okay, so you're probably wondering, well, how did I know which ones from the list I had above had both? We will talk about that in a second. Essentially, molecules that are polar, so molecules that are polar, comma, have dipole-dipole. Okay? So you have to judge the molecule as polar first. Are we making a lot of judgments here? Yes. First of all, you judge the molecule as a molecule, right? Non-metal, non-metal. First check. Second, is it polar? We will go through that. This is polar, this is polar, this is polar. We will go through that process, right? We went through it in the previous lab, but we're going through it again. Then after that, after we judge that it's polar, we'll say it has dipole-dipole interactive forces. Now I move on to hydrogen bond. With hydrogen bond molecules, the hydrogen bonds have, because remember it's incremental, they have LDF, dipole-dipole, and hydrogen bonding. So they have all three. Examples here are water and ammonia. Water has London dispersion force and dipole-dipole and hydrogen bonding. Because it has hydrogen bonding, it also has these other two. Ammonia has LDF, it has dipole-dipole, and it has hydrogen bonding. Okay, because it has hydrogen bonding, it has these other two. Okay, well, how can I tell the intermolecular force in the molecule? Okay, number one, for LDF, like I mentioned, elements that are non-metal have LDF only. Example of that, helium, neon, argon. These are group 8 elements. The second example is Brinklhoff. So I'm giving you a more comprehensive list here for the elements that are LDF only. This is bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. These are diatomic elements that exist as diatomic molecules in nature. So when I draw the Lewis structure here, you can see this molecule is nonpolar. Any molecule that's nonpolar has London dispersion force only. So that's kind of all the theory behind it, right? You can kind of guess your way through your homework, but this is the theory that guides your answers, and that's why some answers are right and some are not. If you have a molecule, it has to be nonpolar. If it's nonpolar, it has LDF as its only intermolecular forces. So that's what I say here. Nonpolar molecules have LDF as their only intermolecular force. The next one is dipole-dipole. For this one here, you have to show molecule is polar. For this part here, we need a little table that says that if your electronegativity difference in the element, depending on the two elements. So look at the two elements making the bond, right? We're trying to judge the polarity of the molecule. So if you have two elements in the bond, for example, hydrogen and chlorine, you want to check for the electronegativity difference. Hydrogen is 2.1 based on this table that I have right here. I brought in the table. This is 2.1. And then chlorine is 2.5. The gap between these two is 0.4, right? So we're usually told that, oh, I'm sorry, I thought that carbons of chlorine. I haven't had lunch. Is that an excuse? Not really, but when I get hungry, things don't look good. 3.0. This is 0.9. Okay. But I always double check myself when I'm working on stuff. So let me move this out of the way so y'all can see. Chlorine is right here, 3.0. Hydrogen is 2.9. So the difference is 0.9, right? So perhaps it was 2.4. This was considered nonpolar. From to one, I think it's like 0.9. The polar. Ionic is, give me just a moment. Let me verify before I go. I'm supposed to verify that, and then something else came a lot now. Okay, so let's see, polarity table. There's another email. It's okay. Polarity. I try to email you guys at once, so table. Okay, I know the table is somewhere here. Why am I searching for that in my email? I don't even know. Give me just a moment. Polarity. I just need the range. Okay. Because I had it in one of my pages, but for some reason right now I just can't think of it. But I think between 0.5 and 0.9 is polar, and then above 0.9 is ionic. Okay. Yeah, because with ionic you'd have lithium, say, and oxygen, right? Yeah, lithium and oxygen would be ionic. Anyway, our focus here, though, is not on ionic compounds. All we want to know is the molecule nonpolar? If it's nonpolar, we have LDF only. If it's polar, we have LDF and dipole-dipole. We could also have hydrogen bonding. Okay, so what we're going to look at here is the bonds we're going to be examining for the most part, because we're dealing with organic molecules. We will have carbon and carbon, carbon and hydrogen, carbon and nitrogen, carbon and fluorine, carbon and oxygen, and then oxygen and hydrogen. These are the most common bonds we will see in this chapter. So I'm going to check to see the polarity. Carbon and carbon is 2.5 and 2.5. The difference here is 0. So this is definitely nonpolar, right? Carbon and hydrogen, let's see. Let me erase this. Hydrogen is 2.1. Carbon is what? 2.5. So the difference here is 0.4. So this is considered nonpolar. This one here is polar. Right on this side, this is nonpolar. And then C and O. C and O, let's see. Let me erase these down here. C and O, carbon is 2.5. Oxygen is 3.5. The difference here, okay. The difference here is 1. Technically, this is here is polar. So this range here goes to a little bit above 1. I don't have that range memorized. Okay. But definitely this CO bond is polar. CO single bond, CO double bond. So CO double bond, CO triple bond, they're all polar bonds. So you want to remember that. And then C and N, let's see. C and N, the gap here is going to be zero point 0.5, right? Because C is 2.5, N is 3.0. C and F, we got 2 and then 4. What's the gap there? 1.5, 1.5. So we have here polar. This is also polar. So I think this may be 1.9. I think it was 1.9, right? I think it's 2.0 and above that makes ionic. So for right now, we'll go with 1.9 because it's bothering me. I'm thinking about it. Then O and H. O is 3.5. H is 2.1. Let me see. What's the difference here? 3.5 minus 2.1, we get 1.4. Yep, 1.4 is polar. So what we see here is, I'm going to highlight the polar ones. Polar bond, polar bond, polar bond. This is polar, 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 and these other two are nonpolar. So we're seeing here that C and C bonds are nonpolar. This is very important, y'all. This is very important from here on. And then C and H are also nonpolar. That means, what does this mean for the future? This means compounds with carbon and hydrogen only will always be nonpolar. Why? Because all the bonds are nonpolar. To have a polar compound, the prerequisite is your bond has to at least be polar. These these are both non-polar, right? I should have written here non-polar. They're both non-polar, and so for that reason, with them both being non-polar, the compounds that have carbon and hydrogen only will always be non-polar. Okay, very important statement right here. You want to write this down somewhere, highlighted like I'm highlighting right now, a lot better. Okay, I have one more thing to show you guys, which is hydrogen bonding. So I showed you the bonds that are usually polar, right? And you've seen that. Now I want to talk about hydrogen bonding. Hydrogen bonding was my best when I was a student because it was easiest to tell. With hydrogen bonds, how do you identify that a molecule has hydrogen bonds? Okay. What you're looking for is a direct bond between the following. Okay, there has to be a direct attachment. It can't be a proximity like, well, we were in the same compound, so it works. No, there has to be a direct bond. First one between hydrogen and oxygen. It can be this way or this way for those of you who are visually specific. Okay, these both have hydrogen bond capacity. That means if you have a compound that has OH in it, it has London dispersion force, dipole-dipole, and hydrogen bond. This is an N with an A. Okay. I can give you guys the molecule water. So we're talking about molecule here, right? I guess if I put it that way, it kind of makes it the same thing. Y'all just flow with me. I'm making it up as I go. Okay, first one. Next one we're going to be looking at is ammonia. Ammonia, this is a structure for ammonia, Lewis structure. You can see here, when you have a direct bond between N and H, it has to be a direct bond. The whole molecule essentially has London dispersion force, dipole-dipole, and then hydrogen bonding. But the requirement, the prerequisite is this bond right here. Okay, just like back here, the prerequisite is this bond. So what we normally say, not to make this complicated, water has two hydrogen bonding sites because it has the OH over here, and look at that, and the OH over there, right? Now this is a non-majors class, so I'll try to keep it simple. In the real majors organic class, they usually check to see which one has the most hydrogen bonding sites. So of course, between ammonia and water, there's going to be competition because ammonia has how many sites? 3, right? 1, 2, 3. Ooh, 3 sites. It gets complicated. So I'm not going to tell you which one wins between the two of them. He's going to tell you there's three sides. Okay, so let's see. Oh, something happened here too. Where this is only. Okay. Let me give you one organic molecule. This is CHHC. I'll put O here. H, H. This is an alcohol. Because of this molecule has hydrogen bonding capacity. That means it has LDF, dipole-dipole, hydrogen bonding. Okay, so let me show you what does not have hydrogen bonding capacity. If I draw this right here, oops, wrong marker, double bond O, H, H. Okay, this does not have hydrogen bonding capacity. Why? This one has no hydrogen bond because even though the compound has oxygen and hydrogen, they're kind of near each other, but they're not attached to each other. They have to be attached to each other. Last bond. For hydrogen bonds to happen, you have to have H and F bonds. H, F. Okay, so if you have HF bonds, then you have London dispersion force, dipole-dipole, hydrogen bonding. So bottom line as a review, you need O directly attached to an H, N directly attached to an H, and then F directly attached to an H. These prerequisites have to be met to have hydrogen bonding. When you have hydrogen bonding, you also have dipole-dipole, and you have London dispersion force. For that reason, we can then say molecules with hydrogen bond have a very high boiling point and melting point. Can you increase the temperature a little bit? I mean, drop the temperature down a little bit, please, sweetie. Thank you. Sorry, y'all. It's getting hot in here. Okay, so let's go ahead and look at this. They talk about London dispersion forces. These are very weak forces. And they talk about how these forces are made. They're telling you that the London dispersion force is a very weak interaction due to momentary changes in electron density in the molecule. So let's decide, okay, that the molecule has an even distribution of charges. So I'm going to draw my molecule like an oblong, right? And it has 4 charges here. Positive. Ooh, okay. I was in a roll. The molecule, I'll just draw it up here. So the molecule has 4 positive charges and then 4 negative charges. This is my made up molecule, okay? So I just show you even distribution of charges. I kind of spread it out, right? Now, sometimes things happen to where the electrons move to one side. Well, it's kind of like you're going to a boy and girl dance and the guys are all in one room and the girls are, or one corner of the room and the girls are in one corner and they're talking about each other and it's like, well, you go dance with her. No, you go dance with him or whatever. Something like that. So sometimes it happens to where all the like charges end up in one corner of the room. Okay, these are momentary changes to where things happen. It can be in the environment. And when this happens, now you have polarization. Remember, polarization is kind of a separation or difference. You have the positive charges all in one corner, the negative charges all in one corner. Now you have a separation of charges. By having this polarization, the left side of the molecule is strongly negative, right? And the negative charges are far from the positive. This side here is partially positive. So when this happened, the change in the electron density or the electron distribution from going from even to uneven distribution results in a temporary dipole. Polarization. Polarization is separating things based on a difference, right? In this case, the difference here is a charge, creating 2 opposite end charges. This then causes, if this happens in one molecule, the molecule will induce the same behavior. It will influence the same behavior in the molecule closest to it. And the way it does that, the partially positive over here will push away any positive in this corner of the molecule to the other end. They'll repel, leaving the negative charge, right? Same thing will happen with the next molecule. Same thing will happen. The positive will be pushed away, the negative will be close to this other end. So in the end, what we end up having now is the positive and the negative attracting each other, positive and negative attracting each other, and this happens in the whole molecule. So we're told that as the temporary charges attract each other, we're getting a temporary dipole and we're getting these weak interactive forces, weak attractive forces. They're not as strong as the permanent dipole. Okay, and I'll show you what a permanent dipole is versus the temporary dipole. These temporary dipoles that make up the London dispersion force. In other words, you have all the guys in one corner of the room, all the girls in one corner of the room, and when you have the separation, in this case though of charges, then the opposites begin to attract each other. And when you have that attraction is called London dispersion force. So we're told all covalent compounds have this London dispersion force. And then rule 2, the larger the molecule, the larger the dispersion. Okay, so let me see, how do I compare? They may have some examples here, or they're showing that to you, right? So it started off in this molecule right here. Something happened to where all the positive charges end on one corner and all the negative on one corner right there. And then because of that, the molecule on the left induces the one on the right. It attracts all the negative charges on one end, and then pushes at the same time all the positive on the other end, right? The change really started in this molecule, but then this molecule influences the molecule next to it. And then before you know it, the whole either solution or gas or solid now has this effect. Okay, then we're moving on. Dipole-dipole interactions are attractive forces between permanent dipoles of two polar molecules. So you have permanent dipoles. Permanent dipole means there is an electronegativity difference that is producing these partial charges. And that electronegativity difference is, oh, sorry, I got another email. Okay, electronegativity difference is due to, yeah, it's the one. Sorry, I got distracted. Yeah, let me regroup. The permanent dipole. So right here, permanent dipole is due to electronegativity difference. Okay. Remember the numbers we had in the periodic table. So we looked at what carbon was. And what was carbon? Let me get it real quick. I tried to write snuff like this, snuff. Fluorine is 4.0. If I don't want to pull up the periodic table, oxygen is 3.5. They decreased by 0.5 on that period. Okay, 3.0, and then we have 2.5. So between these two, we have what? Okay, we have 3.5 here, 2.5 for the oxygen. So the difference here is 1.0. Yeah, this bond is definitely polar, right? And then the one that has a high electronegativity gets the partial negative sign, right? Because that's the one that's more electronegative. The one that has the low electronegativity gets the partially positive sign. So you can see that, right? And so this is showing you a dipole interaction. The partial negative and partial positive wasn't because electrons just randomly moved to one corner. That's not what happens here. The partial negative sign and partial positive are because of electronegativity differences, which exist all the time. All the time. What we looked at here, it can exist and it can correct itself. Okay? But one molecule is always going through it, so it kind of, you see a negative charge in one corner, then you don't. Then you see it, then you don't. So it's kind of like flickering lights. It's on, it's off. It's on, it's off. Here, the dipole charges we see are there all the time. Okay? So the negative end attracts the positive end, negative end attracts the positive end, and vice versa. Hydrogen bonding, like they said, you have a hydrogen atom attached to or bonded to nitrogen or oxygen, nitrogen, fluorine, and there has to be a direct attachment. Of the three forces, hydrogen bonding is the strongest one, but remember they are incremental. And they show you how this applies, right? Hydrogen bonding in DNA. Did you know that our DNA, the double helix structure, the one that looks like the old school phone cord or coily hair, that these lines they have in here, these are actually hydrogen bonding. That's why chemistry is a prerequisite for biology. Yeah, they zoom this part in and show you that the double helix structure is actually held together by hydrogen bonds. So this is good because the hydrogen bond is strong, is a strong intermolecular force. That's the kind of force we want for our DNA. We want it to be strong. We don't want it to be weak where it's easily broken apart by stuff that happens in life. So we see right here, right, the dashed lines show you the hydrogen bond. So please notice, right, this fulfills the criteria between O and the H. Even though it's not from the same molecule, it works as long as H attracts O or vice versa. It's a hydrogen bond. Because remember, it's an intermolecular force. That means between molecules, not within the same molecule. It can be from one molecule to another of the same kind, right? So here, see that? Nitrogen, hydrogen, oxygen, hydrogen, oxygen, hydrogen, nitrogen, hydrogen. Technically, this orientation doesn't work, but if this was flipped over, that could attract that too, but it's just the N is facing away from the O. Okay, so summary. London dispersion, oops, wrong thing. London dispersion force is the weakest of all three. Hydrogen bonding is the strongest. All molecules here, remember, covalent, have this. This includes compounds and even elements like helium. For the dipole-dipole, remember, this is LDF, right? Dipole-dipole has LDF and dipole-dipole, so they are moderate. Molecules that have a fixed dipole or a net dipole, these ones here are polar. They have to be polar. And then for hydrogen bonding, they have to have these exact bonds, one of these three, or a combination of it, OH, NH, and HF. Something I forgot to mention real quick, we've covered it before, but I want to cover it again. How can you tell a molecule is polar? Real quick, I'm going to draw a few. HCl dot 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 dot. C double bond O dot dot. C double bond O dot 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 dot. What else? C H H H H, and then what else? You got these three. What else do we have? H O dot 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 H. Okay, so here's the thing. We have to look at the rules and try to figure out, okay, which of these four compounds are polar. Let's look at the rules we talked about before. Using the geometry, locate your central atoms. I'm going to go through and highlight my central atom. This is my central atom right here. This is my central atom right here. This is my central atom. This is my central atom. Okay. One of the quickest ways to tell is look at the other atoms surrounding the central atom. Do those other atoms, do they match? In the case of oxygen, the oxygen on the left matches the right. The atoms match. Do the bonds or lone pairs around the carbon match? The ones touching the carbon, that's all we care about. These match. Yes, these match. So this is then non-polar. Okay. What else? Let me check to make sure everything is kind of halfway through. Okay. Sharing. What about this one here? Let's check and see. We do have hydrogens that match, but let's look at the electron groups around the lone pair. Around the oxygen. Do they all match? These two match each other, but they don't match this. So when you have lone pairs around the central atom, this is most likely polar. Let's look at the carbon. The carbon over here, this carbon is surrounded by four hydrogens and they're all alike. What about the bonds? The bonds are all alike. Do they have lone pairs? Nope. So non-polar. What about, let's see, right here. What about this chlorine? Surrounded by only one element, hydrogen. It's surrounded by 3 lone pairs. The 3 lone pairs did not match that hydrogen. So yeah, this is definitely going to be polar. Plus, if you have 2 elements only in the compound and one is different, that's already polar. Polar usually signifies a difference from one end to another, right? Here, the difference is brought in by the lone pair. Here, there's a point of symmetry, a plane of symmetry. There's no difference from either side. Here, also, if you look at it, it's technically symmetrical. If you deal with the Vesper model, it is symmetrical. Right here, this side doesn't match that side, so it's not symmetrical. And then you have your lone pairs around the central atom, right? There's so many ways of figuring out polar. Anyway, let's go ahead and move on and look at this part right here. I'm trying to finish this part, take a break, go to the store real quick, and then start my evening recording. Intermolecular forces and boiling point. The boiling point is the temperature at which the liquid is converted to a gas. Right, we have becoming a gas as you apply heat to the liquid. The melting point is the temperature at which the solid is converted to a liquid. So solid becomes a liquid. The stronger the intermolecular forces, the higher the boiling and melting point. So we're seeing here, compounds with London forces only have a low melting point and boiling point. Remember, everybody is so simple. I love these PowerPoints. Compounds that have hydrogen bonding have a high melting point, boiling point, right? You just have to read the PowerPoint slides. So they give you an example here. Remember, this whole molecule is non-polar, right? Because it's non-polar, it has LDF only. This molecule here has OH. So if you're wondering, well, how do you just know? You just know it because you just know it. This is what I do. Let me show you my process. I start with the highest. I'm always checking for hydrogen bonding first. Then I'm checking for dipole-dipole. And if these are absent, then the last one I'm checking for is LDF. With hydrogen bonding, I know for hydrogen bonding, I'm looking for OH direct bond, NH, or FH. Okay, I have H in here, but I don't have O or N or F. So definitely for this one here, there's no hydrogen bond, right? Dipole-dipole. Dipole-dipole, I have to have at least a polar bond. Okay, or the other way of looking at it is look at your central atom, that's carbon. Look at the elements surrounding it. Are the elements all alike? Yeah, so there's no difference. So as far as the elements are concerned, it's nonpolar. Does my central atom have a lone pair? Are there any dots around here? No. So with no difference in the electron groups and no difference in the surrounding atoms, this is non-polar. Therefore, no dipole-dipole. Since it's a molecule, by default, it has LDF only. This one here, starting with hydrogen bond. Do I have OH? Yes, I actually have 2 of them. Okay, I don't have to check for the other ones. Since it has OH, it has hydrogen bonding. That means it also has dipole-dipole. It also has LDF, right? So when you're trying to boil water, you're going to need a lot of temperature here to break through all of these forces right here. Gotta boil, break it apart, break this apart. Okay? And then for methane here, let's see. For methane, it says, oh, it's much lower because you're only dealing with one intermolecular force. Okay. So we're moving on, getting close to the end. Intermolecular forces and melting point. Both propane and butane have London dispersion forces, and they're nonpolar compounds. Nonpolar bonds, remember, right? CC is nonpolar. C double bond C is still nonpolar because what are the elements? C and C. And then C triple bond C is still nonpolar, right? And then we checked earlier, C and H is also nonpolar. So if our compound has C and H's only, guess what it is? Nonpolar. I'm hoping to say this a lot so that it sticks, right? For that reason, even though these are 2 different molecules, they're technically both nonpolar and nonpolar. Why? Look, take a inventory of the elements present. There's only carbons and hydrogen. Therefore, it's nonpolar. Carbons and hydrogen only. Okay? Okay, let's see. What else? Nonpolar, nonpolar. Then we have a low boiling point and a low melting point. But now we're comparing apples and apples, the left versus the right. Since the right side is a larger molecule, because it's a larger molecules have higher intermolecular forces. Okay? If the molecule is larger, whatever intermolecular force you have, you see a greater effect of it, a greater effect. Okay, hold on a second. Okay. Now with specific heat, I don't know why we have specific heat here. We're not doing much with this specific heat. Let's see. I'm trying to see if we're going to be doing anything with this. We're not doing anything with specific heat. So I can say we're done with this chapter. Oh, great. Yep. We're not doing anything with specific heat. So essentially, this right here is the last part of the chapter. That's it. So I want to work on a couple of questions here just to kind of a quick review. I'm going to go through the different functional groups, right? Because you guys have been going over that already, I know, in your homework. So I'm going to go through three carbons. How about that? Like this, like this, like this. Just random ones that I can think about with 3 carbons. Okay? It's one missing here. 1, 2, H. I'm trying to make sure the carbons are surrounded by 4 bonds. 1, 2, 3, H, H, H. And then what else? I'll go with this aldehyde. I said 3 carbons, right? 1, 2, 3. 1, 2, ooh, 1, 2, 3. 4 bonds, 4 bonds, 4 bonds, okay? And I'll do a ketone like this. Carbon, carbon. 1, 2, 3, 4. 1, 2, 3, 4. There. Okay. Make sure when you're drawing your structure, the carbon is surrounded by 4 bonds. Then I'll do a carboxylic and I'll do an ester. A carboxylic is 1, 0. Oops. I didn't do an alcohol. I just thought about it. I'll do an alcohol in the middle. Bonds. Make sure each carbon is surrounded by 4 bonds. And then right here we got where was I? Oh, I'm gonna do an ester here. So that's like this. And then C, then I got an H, and I got an H, and I got an H here. Okay, give me just a moment. Lone pair, lone pair. I have to put in the lone pairs. Oh, I'm not obeying the octet here. 1, 2. Let me see. I'm rushing so I can respond to emails. Hold on, y'all. I'm trying to multitask, you know. Doing all this stuff takes up time. That's why I can't get to grading in time because I'm trying to do so many of these other things. That's okay though. I get to it eventually. I get to it. Okay, I want to do one more for the alcohol. So the alcohol is going to be OH. Then I'll put 1 here. 1, 2, 3. 1, 2, 3. And then here. So each of these carbons is surrounded by 4 bonds. So what I'm going to do here is I'm going to go through and check for the OH. I'm looking for the OH. First of all, these first two don't have an O. There's an O here, but there's no OH. Okay? But this will be my central atom of interest. This one right here. Since it has an oxygen. This one will be my central atom of interest since it has an oxygen. Okay? So what I do, when I'm looking through the formula, I'm trying to explain to you what I'm doing. I'm looking for, they call them heteroatoms. Okay? I'm looking for heteroatoms. Heteroatoms are atoms that are not hydrogen and not carbon. So these are like oxygen, sulfur, chlorine, nitrogen, etc. Just non-carbon, non-hydrogen. So in the first two, I didn't find any. In the second one, I found an oxygen, and then I'm looking at the carbon attached to that oxygen and making that carbon my carbon of focus, my central atom. Okay, so this is the logic I'm using. Once again, I found me some oxygens. This carbon will be the carbon of focus. I found oxygens. This will be the carbon of focus. I found an oxygen. This would be the carbon in focus. Okay. Organic chemistry is kind of focusing on carbon and the bonds it makes with others, but the focus is carbon. Okay. What was I doing again besides that? Oh, yes. Now I'm looking to see, do I have hydrogen bonding? I'm actually going from strongest to weakest. Hydrogen bonding is OH, right? NH and FH. So the ones that had O's in them, are they attached to H's? Not here. So I'll say no HB here, right? No HB. No hydrogen bonding because the O is not directly attached to an H. What about this one here? I see two O's. Neither of them is attached to an H, so no HB. There. Oh, look at that. This is another O. It's attached to an H, so I can finish this one right here. This has a HB, therefore it has a DD, has a LDF. Okay? That goes with this, just to kind of... Okay, what about this? Look at that too. This is my alcohol right there. This has a HB, it has a DD, it has a LDF. Okay, so you see that? Yeah, there. This one has no HB. Okay, let's see. So now that we've decided which ones have HB, we're now moving down the list. Which ones have dipole? You want to find a central atom. We know for sure with dipole, find a central atom. I picked the central atom I'm going to be looking at, this one here. Another way of finding dipole, if you have an organic element, organic compounds usually have carbon and hydrogen. If they have a third element in it, like sulfur or oxygen or nitrogen or chlorine or fluorine, just a third element in it is most likely polar. Okay, so I see that there's an oxygen here. I can jump and say it's polar, right? It has no hydrogen bonding, but it's definitely dipole because of the oxygen here. Okay, the other way I can look at it is this carbon here. This doesn't match that and doesn't match that. You can use that rationale either. So even though it has no hydrogen bonding, it is definitely dipole because it's polar. Same thing with this carbon here. This group matches that group, but doesn't match this group. So definitely this is dipole. The other thing, it has a third element that's not carbon or hydrogen. So two reasons why it's dipole. Okay, it's that third element situation. Third non-metal. Here we got the third non-metal. I'm giving you guys more than one way to be able to pick the right answer. Oh, this one here, does it have that third non-metal? Come on now. You see it over here and over here, right? The other thing you can say is this group doesn't match that group, doesn't match that group. Therefore, this one here has dipole. We know if it has dipole, it has London dispersion force. So we can finish this one up. This has London dispersion force. Also, London dispersion force. So we know for sure it doesn't have hydrogen bonding, but it has these two, right? So I'm going to erase that. It only has these two. Let me draw a little box around this. See, right there. And then this one here. And then this one here. Oops, I did the wrong thing. Okay. So we're now left with these two. Okay, they don't have interesting third non-metal elements. They don't have that. This one here has a double bond, but not enough to make it polar. Not significant enough to make it polar. There's no OH, there's no NH, there's no FH. So these just have LDF only. So interesting. LDF only. Okay. Yeah. Ta-da! And that's the end. We're not doing anything with these. I forgot to remove them from the slides. Okay. And that is the end for this. I'm happy I'm finally done with this. I've been trying to record this. This is my third time. Something always happens. I hope I pressed record because